Okay, now let's start. Welcome to the first CGD seminar for this year. It's my pleasure to introduce Professor Ming Cai from Florida State University. And Professor Cai got his PhD from University of Illinois, and he joined the FSU in 1999 and got the full professor in 2010. And his work mostly related to the climate dynamics, and he also has many unique views about climate dynamics. One of his work is called CFRIM, the Climate Feedback and Response Analysis Method, which is a nice way to decompose how the climate feedback is and what's the contribution of each of those feedback processes. He has published over 100 peer-reviewed journal articles, and he has been the editor for the Journal of Atmospheric Physics, Atmospheric Science. And he also has been the director of a large-scale climate dynamics program at NSF. And today, he is going to report his most recent work, which is entitled A New Paradigm for Principle-Based Adept Prediction of Global Warming from Climate Mean States.
All right, thank you. Yeah, thank you. And thank you for inviting me here. And it's always a good pleasure for me and to with NCAR and also with Boulder. And this time I have a mixed feeling, and because I have less face to recognize, and but very happy to see young people here, and which means the continued growth of our field. And that's I guess I feel much better and to see young people here. And I should say that it's a new study, and it's based on 4 papers. First, only focus on the first one, but the foundation is the one which published as part 1 in JS this year, and you can download here. Then we have part 2 and part 3, and let me go on. So the objective of this work is okay. This outline, okay, a quick overview of established climate feedback framework, and then we talk about the ingredients for predicting global warming without running model, which also is based on the principle, and also talk about tools and data needed for doing so. And next 3 is the 3 major ingredients for predicting global warming. Of course, you need to know what's driving the climate change. The second one is we call the energy gain kernel. This is the core part of the prediction, which is published in part 1 in JS. And next one is we still need non-temperature feedback. So this involves approximation. Then I'm going to present the results and our prediction and validate. Okay, and I'll give a conclusion remark. Without this approximation, this will be 100% principle based. Because of this approximation, there is limitation. So I'm going to go quickly, like what kind of limitation. You cannot apply this for any prediction, okay? And why work for the greenhouse gas induced climate change, okay? So the objective is put forward a principle-based framework for relatively accurate prediction of global warming and its spatial pattern, not just a global mean value, and also include the spatial pattern in response to anthropogenic greenhouse gases from climate states without running model or statistical analysis. Then we're going to predict and validate 2 things: observed warming from last 40 years, and also we're going to reproduce global warming projection made by each climate model. So effectively, we also try basically test this, validate this method many different ways, okay? And so-called principle-based, I want to see here, the one explicitly used in this new paradigm is the radiation law. radiation transfer model, and also energy balance model. Energy balance model not only for perturbed climate, also for mean climate state. Okay, so the principle we implicitly use, of course, you need is whatever we use for climate model, like Navier-Stokes equation, for infrared motion, for ocean, ice model, cloud physics, and so on. Okay, so those things here is implicitly used, not directly. Okay, and here, let me start from the feedback. The feedback concept is first introduced in the electrical engineering. Harold Black designed the first electrical engineering feedback circuits in 1934. So the feedback concept is here, this diagram here. Let me explain this diagram here. So basically, here, this is the voltage, input voltage. By that time, there is already amplified voltage. Like my voice amplified through amplifier, you hear my voice. But this amplification is not stable. So they want to introduce something control the output volume. So also the output volume we consider signal, original signal, which is my speech, and also noise, and also distort the signal. So they go through this, the key thing, voltage here, and the voltage, if the voltage have fluctuation, goes through the feedback process. This is with the computer chip effectively, okay? And the feedback circuits, they call it beta. Beta is amplification or de-amplification. If the voltage too high, reduce. If too low, increase. And so beta, you see how the work is this beta serve as a parameters, multiple the voltage, give you new output voltage. So the output is a very stable output in terms of voltage. So that's the feedback system. And in our field, Hansen et al., 1984, was first introduced the feedback concept for climate study. He was first. And Weatherall and Manabi in 1988 was the first who formulated this method, mathematical model, to capture the instance, okay? The model itself is very familiar here. This is called individual feedback parameters, okay? And the Planck feedback related to the surface temperature change, albedo and water vapor, laboratory is air temperature, and clouds, okay? So that's the feedback equation. And Pixel and Out, 1992, drawing this diagram in the fashion of electrical engineering feedback circuits, okay? But you notice that in order to draw here, let me see. The input is change energy input is external energy. Like when you increase CO2, the energy increase, a change in energy. But the output have different units, temperature, called surface temperature. So in our climate feedback study in the literature, output is surface temperature change, not air temperature, surface temperature change. So that's output. Res looks like the feedback, so individual parameters here. So this also includes biomass feedback, is CO2 feedback, okay? And but the usage of the equation similar to the amplification formula in the electric engineering is based 2007 says more figurative, it's more symbolic, okay? Besides this, so the importance of this feedback concept is very important. Like this one, sorry, oh, okay, here this I was warning here, do nothing about it, and so let me see what. Okay, let me go over here. So basically, you regard here, through the feedback, you know exact output voltage you have. In principle, given external forcing, if you know all this, you can directly predict temperature change from the feedback analysis. However, these feedback parameters rely on the partial derivative of climate system. Those derivatives may not exist. and also very complicated. So in practice, we use the predicted temperature to estimate the parameter. So in that sense, it's only purely for diagnostic purpose. Even though we think there are prediction power, but actually in reality, there's no prediction power, okay? And here, so if I put this here, if we really think the climate feedback, establish the climate feedback framework is something like electronic feedback device. You can think this is more. So the thing here, our input energy in our formulation does not change, just external energy. So what is change? So in terms of electrical engineer, voltage does not change. So what gets feedback is currents. Okay, so by changing currents, you need resistance has to be changed. So effectively, our feedback analysis is more like nowadays, like cell phone or the other thing here. You may have this kind of. I think Google ChatGPT tell me that there is such a device. Because it's current sensitive, you change the material of the chip, something, then resistance change, then change the currents. So you don't have to change the voltage to get a feedback, okay? So effectively, if you do the parallel thinking here, all the feedback parameters more like resistance. Your currents is temperature change, surface temperature change. And the voltage is the external energy perturbation. So let's see here. Actually, it makes sense when you change the water vapor, you change the clouds, you say, oh, and because they absorb long-wave emission from the surface, I increase resistance of energy going out. So that makes sense. So effectively, our climate more like change of material, depend on the temperature, okay, here. And also you can see that I change the surface albedo, also make the Earth easily absorb solar energy, which is effectively more resistant to long-wave radiation. So that's also okay. So except this laboratory feedback. Laboratory feedback is temperature. So it's very difficult to conceive that the air temperature change equals to some kind of resistance. So actually, the whole thing here, the major work is how we represent temperature feedback, particularly air temperature feedback. So that's the key to turn things around, okay? So everything else, we haven't changed. So it makes sense, okay? And so here, turn out, our climate feedback indeed like electronic circuits, feedback circuits, except without chip. So I call this Mother Nature's feedback circuits for climate change. Okay, so that's the components. Let me introduce one by one. So this is all the ingredients for predicting climate change without running model. But if you have a question, you can always interrupt me, and I want to make sure that's clear. And so first, you need input energy. So that's so information about the future. You need to tell me or tell us how much CO2 change. So we can calculate any input to the climate system. Okay, I put 1D, it's vertical. It's not like one thing here, vertical profile. If you do this, all the gray points, you get 4D. Okay, so energy perturbation is just not one number. It's a 4-dimensional, a 3-dimensional thing here. But for the feedback circuits, here only we work on the one vertical column. Okay. Next one, you need to know non-temperature feedback. I'm going to talk about what is non-temperature feedback shortly, and just say non-temperature feedback. So which is albedo and water vapor, clouds, and so on, include convection and the other thing. The third one, which is amplification by temperature feedback. Okay. So the product of 2 and 3 is beta for the first feedback circuits designed by the Black. Okay, it's feedback. So here, the units, no units, just amplification, no units. Okay. And last one, the emission perturbation of each layers. Okay, individual layers. Okay, so that's the energy output. Okay, and so energy output still you need to relate to temperature change. How then? Energy emission output actually is by radiation law is very straightforward. All you need to know, you can calculate the emission perturbation per 1K warming of individual layers. Okay, which is this derivative. That's very well-defined derivative, and the temperature change is total emission perturbation of individual layers. Okay, so this 1D means one-dimensional. You see, energy feedback circuits is two-dimensional. Okay, it's not 1D. So, and if you count all the grid points, it's four-dimensional information. So that's the only difference is the temperature feedback. It's a K. And so here, then this is I can write the energy balance equation. Simply the denominator of the equation, input of energy, which is 1 total amplified, okay, multiplied by beta is which is 2 times 3. Okay, that is the total energy perturbation equal to output 4. You divide by 1K per this emission perturbation per 1K warming, you get a temperature change. So mathematically, effectively, this circuit board here is energy balance equation. Perturbation energy balance at each layers, include surface layer, depend on I value, I, okay? Okay, and so right-hand side, left-hand side, energy emission, perturbation. Right-hand side, energy input. So this external energy input amplified by this two. Okay, so this number JJ is a total amplification by all non-temperature feedback. Non-temperature feedback include change in water vapor, change in albedo, change in cloud. Those through radiation process. I call them radiative but non-temperature feedback. Other is the non-radiative process. Convection and dynamics. You need to run Navier-Stokes equation and ocean dynamics, and also ocean heat storage term. So they all include here, number JJ, okay? And one thing I want to point out here, if you multiply this in here, you can see each one is energy perturbation, okay? So you can say energy perturbation due to water vapor change, due to cloud change, due to albedo change, and so on, due to external forcing. So effectively, this is the true beta in the eye of black, okay? The GIG, okay? Energy gain kernel. Oh, sorry. Okay, so of course the temperature change, just based on energy balance equation. So far, at least I haven't made any approximation. Assume all the we know, no approximation. So this is once you know all this here, GIJ, nominal JJ, you can predict climate change from top atmosphere all the way to surface. Okay, not ocean, deep ocean, not ocean temperature, but include surface temperature. Okay, and so the tool you need, the first principle we use is the radiation transfer model. So that's the only tool we need. If without running model, we still need to run this model. But this model is a time independent model. You see, when I say run model, I don't do integration. Half hour, whatever time step, no time step involved. So this is the only model we need. And of course, data, we use climate state, everything, 3-dimensional temperature, water vapor, clouds, I think plus ozone. I think this is something disappear plus ozone. Oh, that's the screen here, okay? And also you need a concentration of CO2 and methane and other things, minor gases. And also need a 2D surface pressure. We do need a surface pressure. And that's tells you how much amount here and the surface albedo field. That's all we need. And so first we how to calculate the energy perturbation due to CO2 increase. So we just run the radiation model twice. One with whatever the climate state we want to begin with, plus the corresponding CO2 concentration. Now we are seeing here, this is the current climate state. Now you increase CO2. So we say how much energy introduced by just increase CO2 without changing clouds, without changing temperature, without changing everything else. So you calculate twice. The difference is that energy amount. Okay, that's the energy amount. Here, I give you the example, okay? So this, when you just, this is quadrupling CO2, by the way, this is based on CES model, quadrupling CO2 for pre-industrial simulation, 255, okay? So when you quadrupling CO2, so you put global averaging 1.7 watts energy at the surface. You see here, you see the mountain, cold place, also even desert, because there's very little water vapor. When you put CO2, all the forcing at the surface, where you don't have water vapor in the air, okay? But where you have water vapor in the air, actually in the atmosphere, not at the surface, okay? And you see that's cold, actually negative, is negative here. You add all atmosphere and the surface equal to TOA, okay? So it's 5.1 watts. Probably you recall that in the IPCC report, you say double CO2, 4 watts. Why you quadrupling CO2 5.2? Here, we didn't do a stratosphere adjustment. Stratosphere is cooling. So that 5.2 includes the stratosphere cooling part. If we calculate at the troposphere level, which is the IPCC record, would be 8 watts. Okay, more like 8 watts per meter square. So that's the total energy. You just increase CO2, only 5.1 watts in some global mean, okay? So that you also have a spectral pattern as well. So now we go back to how we get the energy gain kernel. First, we contrast the so-called Planck feedback matrix. So this derivative is only derivative well-defined, okay? PRP also using this derivative. They call temperature kernel and so on. So here, how this work? Each layer, I increase a temperature by 1K here at this level, which is about, I say, 825 millibar, okay? Then you calculate, you radiation model would automatically give you cooling rate. Of course, you increase 1K warming here, that layer emits more energy. So cool, positive means cooling, thermal cooling. So the cooling neighbor temperature has not changed in this calculation. So neighbor absorb that energy, partially, does not go out all the way, okay? Partially absorb energy. So therefore produce cooling. So this measure is always diagonal. Okay, now you do inverse of this matrix. That's inverse matrix. Inverse matrix is physical meaning here is you put 1 watts energy here, produce cooling, warming all the way. This is just inverse this way. So this is very rare. You have matrix whose inverse always positive. Okay, that's also a unique thing. Okay, and so that's one here. Turn out this is the work, and I should mention that. And 2010, I visit NCAR, and we do collaboration and use this method. And so that's published here. By that time, we call this C-frame. The keyword is feedback response. This is response to unit energy perturbation. Response, not feedback. Response means results, not response, but it's temperature, the unit temperature. Okay, and so it takes us almost 16 years. Okay, to figure out for prediction, make use for prediction, we have to write this in terms. We take diagonal elements out of this inverse matrix. This become more physical, meaningful, more like feedback circuits. We call it climate energy gain kernel. Okay, this kernel is different from the other kernel. Let me explain next. First of all, this energy gain kernel, like inverse of matrix, is a solution of climate model, just without other feedback, just with temperature feedback. It is solution. Solution means you run the model to infinity. 100 years, that's what you get. Okay? So there is time integration built in here. So this is not like other kernel. This is a solution kernel. Okay? And the solution is expressed into here. So here, for example, add 1K energy, 1 watts energy here to this location, 800 hectopascal. After you run the model, you will see that energy become 3 watts per meter square amplification. Even you only add energy at 100 hectopascal, all other layer gain energy too. Okay, so that's energy gain at each level. So they're in 2 parts. Diagonal is amplification rate, energy you put, amplification of that, and also energy gain from input energy perturbation at other layer with temperature feedback. So temperature change with temperature feedback. Okay, and the horizontal, the 2-dimensional here, the horizontal means here, this is 800 hectopascal energy gain. So here, even you put energy at 200 hectopascal, you still gain energy. So energy is not at this level. Through the temperature feedback, 800 hectopascal gain energy. Here you put energy at 800 hectopascal, they amplified, becomes 3 watts. So that's the meaning of this horizontal axis. Okay? So no, you can do global. This is a vertical. Each location you have such matrix. Each location you have this matrix. So this is 4-dimensional signal. This example, I think I use global mean value here. Yeah. Depends on location. So that's our part 2, part 3. How this matrix change with location depends on how much water vapor in the air in time in state, how much cloud in time in state, even surface pressure. You see, you have a higher surface pressure, high mountain, very little gain. In deep tropics, during over storm track, the gain is very, very large because you have more clouds. So really depends on how much the atmosphere, the amount of absorber distribution. And also very interestingly, also depend on temperature as well. Believe it or not, they also depend temperature too. And depend temperature also not straightforward. More absorber, more gain, more amplification. But higher temperature can be less gain, depending on the amount of water vapor. That's very, very complicated. In nutshell, is unfair window because the emission is temperature dependent. Absorption is fixed. You see, water vapor always has channel here. So these two make the temperature dependence very complicated. So that's our part 2 material. And yeah, go ahead.
So when you say that you're running the climate model to infinity, it's like a 1D radiative transfer at each location?
Yeah. Effectively, you can run 2D, our model, because each grid point is independent. So you get the same thing. Yes. But when you run the climate model, you have to keep your clouds change same. Your dynamic heating rate also same. So advection, convection, everything same. That's what you get. Yeah. We test this one. We test this one. You're right. And so here, that's the equation we have here. So now we see why this is the solution. So let's demonstrate this again. That's exactly what the equation here. Suppose we don't have other feedback. Water vapor same, cloud same, and albedo same, and dynamics, heating rate, advection, everything same. So we should number GJ equals 0. Okay? So you do this, and that's same feedback. You see the only thing here, the another matrix, non-term feedback disappear because equal to 1. It becomes unit matrix. And so you give same energy perturbation, amplification due to temperature feedback, and emission, everything the same. Okay? Okay. The only thing that you don't have 2 here. You don't have temperature feedback. So that is you have less amplification because other thing. Of course, the other thing can be negative, also can be de-amplification too. Okay, let's see what's happening. Okay, we don't know that yet. And wrong way. Okay, so now after this stage, all we need to predict final warming is somehow figure out amplification by non-temperature feedback. Okay, that's all we need to know at this moment. So let's look how the amplification as manifested in the CES model, this anchor model for CO2. Remember here, the TOA, the energy, 4.25 watts per meter squared. Now you run the model and run the equilibrium. So you run model in 2 ways. First, don't let everything else change except temperature change. Okay. Sorry. I think this is the reason I want here. Okay. You see the energy here, the column integrate energy, not the TOA energy, is 70 watts per meter squared, 10 times stronger. Even though at the TOA, because it's balanced, still 5.2, but inside is 70. If you count how much individual layer get energy, amplification, 70 watts. And if you run the model, actually don't run the model, it's just more diagnostic because the CM model already gave the answer. Tell me how much water vapor has changed, how much ice has melting, how much convection has changed, dynamic has changed, right? Tell me everything. So I do diagnostic. I say how much energy amplification you get? 5. Global mean about the 5. So this is the 14 time amplification. Without temperature feedback, it's 5 times. But with this energy, already amplified by the other non-temperature feedback, you calculate again, 240 watts per meter squared. And the TOA is still 27, okay? Because that's energy output. But inside, if you count individual, how much, you just don't do cancellation, how much energy individual layer get? 240 watts. So here, I think that's one way to really to sell the climate science. On averaging, Earth system only gets energy at the TOA is from sun, 240 watts. You see, you just double CO2 by all the feedback, you get another 240 watts. So that's really remarkable of energy the Earth system gain through by just quadrupling CO2. Okay, so here you compare these 2 panels, immediately you just know temperature feedback alone, you underestimate warming. You do need temperature feedback, but this amplification is 10 times. The reason is not same rate because the non-temperature feedback has cooling, okay, has cooling, convection has cooling, and so on. I know there's something we can go here. So next one, this is the recap what we learned so far about temperature feedback. And this is the entire feedback circuits right here. So external evolution of temperature temperature change in time, evolution in response to external forcing already captured by EGK. So all we need to do to predict final warming is to figure out amplification by external energy perturbation by non-temperature feedback, which is rather time dependent, at least in this framework. Okay. Suppose somebody tell me temperature, water vapor would amplify by a factor of 2. I just use that 2. And the cloud factor of 1, I use there's no amplification. Okay, 1.1, I do 2 times 1.1. You just time, okay? You just do all this add together. That's how you get, okay? So next task to say how we know this, okay? So this, let's see what's this feedback, non-temperature feedback diagnosed from the CS model simulation, okay? So this is basically this vertical profile taken from an tropical one location, okay? From the model. You see, so here is include everything here. So include x, integer x, water vapor, clouds here, I submit here, I divide by external forcing at layers, okay? Positive mean same sign as external forcing. Negative mean opposite sign, even include 1, okay? So this mostly reflects here, you have a convection, I think all the negative here, a little bit more, but you can, generally speaking, in tropic you have convection. What the convection does, remove energy from lower troposphere, move to upper troposphere. So that also change energy. And also you have a advection term, and also there is water vapor and actually cloud, actually the CO2 forcing in an atmosphere is negative. But the water vapor also negative. Negative is positive. So that's the reason why here you don't see convection. So it's more complicated. So basically, I'm saying here, in order to do this, yes?
This might be a very naive question, but where is the Planck radial feedback in this? So the temperature warming, because I don't see that.
Not yet. I'm just amplification. Remember, I only figure out amplification.
So you're not looking at the Planck
I haven't done that yet. Yeah. So I need to remember like feedback. You need to know amplification before you do temperature change. So to figure out nominal JJ, you remember the principle so far, at least in the math here, explicitly use radiation. Okay, temperature change, radiation here, and also energy balance. So I write the whole circuit satisfies the energy balance. So there are the physical law, cloud physics, ice model, ocean model, and dynamic model to core model to do the vection, to convection, and you also need convection parameterization, and so on. Also, you need cross collaboration, whatever you need to predict water vapor. Okay, use that you need landing heating, everything you need. Okay, so all this principle is in here. Okay, that's the reason why so far here we diagnose from the model. Model gave us effective net results of here. Okay, you do need this thing to predict climate change. Okay, so next here, so this is I write a perturbation energy equation, just here. So I'm trying to do. No way we can figure out all other model because they also interact with each other. Ice model interact with ocean model interact with atom model. They all couple together. You follow here? How we do know this? So one idea is, can we borrow the mean climate state? Mean climate state satisfies this law. Okay? So now that's what I'm going to do next. Okay? So instead of doing perturbation, I'm going back to climate state. So how this law represented by this, how this physical law governs the time mean state effectively. Okay. And so to do this, so we reduce the goal here. Remember this, if we know this here, we can run entire 3-dimensional warming, cooling pattern. Okay? So here I just focus surface. I say how the surface perturbation equation looks like with the factor of non-temperature feedback. Okay? So that is here, the equation is not clear here. But anyhow, boil it down, if I do graphically, non-temperature feedback is a vertical profile. You have vertical profile external forcing. Remember, external forcing also has vertical profile, not at the surface, vertical profile. You multiple them together, you become new profile. So that's vertical profile is the amplified external energy perturbation by non-temperature feedback. Okay? Then you multiple by EGK surface rule. So that's brings the energy from this layer to surface, from this layer to surface. And of course, also amplifies surface energy perturbation. So that's how mathematically done. So if in terms of equation, so that's the equation here. So now, here, this is now approximation definition. So this is actually energy due to what we were changing, due to dynamics, due to other things here, and also CO2 change, and gained at the surface. The denominator is energy gain at the surface without non-temperature feedback. So ratio is the effects of non-temperature feedback. So that's the key, okay? Ratio is here. So far I haven't done anything yet. So here, now let's see how that looks like. Okay, just with still diagnostic, without prediction. So here I do this. So this external energy at the surface, I showed before, quadrupling CO2, 1.9 watts. Just direct CO2 forcing at here. Okay, you see this different color here. Then after temperature feedback and gain at the surface, and also brought down the energy forcing at the, from air to surface. That's all they have, 12.4 watts, 6 times stronger than this one. We can predict global warming from this panel, but this is no temperature feedback. Okay. So now, now we calculate this ratio. So now this is gain of energy due to non-temperature feedback and external forcing at the surface divided by this one. You calculate this way. Okay, this is the formula how I calculate. That's here. So basically, you need another factor of 3 in terms of global mean. Okay, and also you see the nice pattern. You have ice melting here, probably the amplification is larger in the high latitude. And also, but we know in the Antarctica, very little ice melting, still very large, toward energy transport. And also, you know the water vapor increase in the tropics, so amplification is slightly larger here. But mostly due to ice albedo, energy transport here, you have convection strong here, because this cantilever convection in subtropical ocean is very small. Okay, you do have warm ocean, warm land, land over land can larger, and the ocean is smaller. Again, this is not this is credit to CS model. That's what you did. That predicted. So you tell me that the model tell me that I do need another factor to accurately predict warming. So now how we get this factor? So now I say we can learn from the past. So that's what we learn from time in state. Okay, so that's I think I need to do this off here. Okay, so this is the energy balance equation at the time in our past. Okay, not the future. So I write in the form differently. Maybe you don't see this form, but when I rewrite the equation in this form, this is still energy balance equation at the surface. I have in mind amplification. Okay, so the sorry, let me see. I think I wrong. So that equation in terms of if you translate in English, numerator is energy output in time in state at the surface. 3 forms: evaporation, long-wave emission, seismic flux. If an ocean, global ocean have a storage term, ocean also transport the ocean. Okay, -1 is amplification to income solar radiation. In timing state, the external forcing is from sun. So that's external forcing. Okay. So in terms of global mean, so that's the climates here. So that this picture you well known here, and from Travers, if Travers here, this is a surface version of his energy balance equation at the mean state. And so you surface get net solar radiation global mean 160 watts, 168 watts. We call this greenhouse effect because as we have absorption and warming here provides 324 watts. As a result, in our balance, the surface has output so much energy, 492 watts, not 168. So that ratio is about 2, global mean sense. Now let's see how that works, whether we do analogy, okay? So the mean state, so this perturbation equation, we write this form, okay? This term here is equivalent to solar energy input. Here, this term, okay? Okay, so this equivalent to amplification. So that ratio. So our points, our analogy, okay, if we want to learn past, the one thing we can learn past, assume same amplification rate. That's the only thing, this assumption, okay? So we assume the amplification is the same, okay? G times this external forcing after temperature feedback, actually at the surface, without non-temperature feedback. So all you need to apply this one. Then you figure out the surface emission. So let's see how that works, okay? So now this everything here in this slide is from timing state. So this is downward radiation at timing state. This is the mean state of solar radiation absorbed at the surface. So this is the ratio here, okay? So here you can think that I want to say why Navier-Stokes equation and ice model, cloud physics, everything in there, you can think that. Suppose you have less albedo, which means less ice in the polar region. This energy will be larger. More snow, more ice, the value is small. Okay? And here you have more clouds in the tropics, in the equator, value is smaller because of reflection. Okay? You have more water vapor, it's larger. So downward radiation, or same thing. You have downward radiation, you have more water vapor in the air, more downward radiation. Okay? You have more polar energy transport, this value is larger. Okay? And you have a cloud, same thing here. So the net effects, that's amplification. Okay, that's amplification to this external energy. By this Navier-Stokes equation, by the dynamics equation here, probably not include ocean, okay, because we only consider air. Okay, so that's amplification. Now, we just compare, okay? This is what I showed before on the previous slides. I think my time, 11:49, wow, my God. I may need to go fast here. And so here, this is CO2 forcing without non-temperature feedback, okay? So this diagnosed the amplification from actual model simulation. This from timing state. Do you see these two patterns very similar, except amplification rate is slightly smaller? Okay, okay. And let's do the correlation. So let's show the horizontal axis is from this panel. Vertical axis from this panel, each grid point. The correlation 0.91. Without global mean, is 0.51. Still, because they don't have oceans, the less here, okay? And so I want to move a little bit fast here. So turn out, so that's the equation we're going to predict here. This is based on principle 100%, except this one I estimate from the timing state, from the past. So we learn from history, effectively. That's what we learn from history. Okay? And so this is observed warming. So is this 40 years trend, you can see the difference. External forcing at the surface, only 0.13 watts. So it increased 70% CO2 in the last 40 years, from 355 to 385. Okay? But after this non-temperature feedback, become 0.8, 6.6 times stronger. Okay? This we inferred from timing state 1980 to 2000 without using future information. So you multiply these two together, divided by 4 sigma T cubic, is warming. This is our prediction. This is actual warming. As far as global mean concerned, very, very accurate, up to second decimal. Okay, and of course, remember, observed global warming caused by aerosol, besides CO2, methane increase, aerosol, volcano eruption, also internal variability, but include oceanic internal variability. So that's the difference. The difference mostly is over ocean, and also there is PDO signal because we just passed hiatus. There's still residual of hiatus, negative phase of PDO still there. So basically, we are seeing that based this alone here, because our prediction is pure CO2, we can 100% confidence tell public the observed warming in the last 40 years is due to CO2 increase. Okay, who caused the CO2 increase? That's the public debate, okay? But that's true. Internal variability does not play a significant role here, even regionally speaking is there. And next, we do compare historical simulation, predicted by each model, climate model. So this is their sketching here. The median value 0.53, far, far higher than observed warming. Only few model in that range, close, below 0.45. So it's 25% there. This is our prediction. Okay. So also next we had to do another matrix to say so basically this is observed warming pattern. Each model historical simulation have a pattern. We do correlation with this pattern. So that's the value of correlation here, the top line. Our correlation is 0.61, 0.69, okay? The bottom one is we remove global mean warming. So that's how inhomogeneity of the warming. Our prediction is less because we don't have ocean response, they're not here. But all the model still not perfect. And I would say here it's okay. And the prediction is 0.56 in terms of regional pattern. Okay, some models actually less than what we have. Only one model. So next, we do same 6 model. This is the ensemble mean. We do ensemble mean, and so we use ensemble mean, cloud, everything else. We calculate forcing, and we also calculate EGK. Our EGK is based on ensemble mean, EGK, okay? And this is ensemble mean, pre-industrial simulation amplification. This is our prediction, okay? We have a large error here, and the ocean. So this again show very familiar pattern, like observation. This is very remarkable. Ocean, all the models have this kind of pattern. ACC cooling, upwelling, and here some models stronger. But the only difference from the observation, the model have ENSO response, strengthening of ENSO in response to CO2. Okay, so this is box whisker plots here. Okay, so our model also have intermodal spread. The intermodal spread because we built in pre-industrial run of climate model. They all different, but not that different. So therefore, our intermodal spread is smaller than actual intermodal spread of the Sim6 projection. The intermediate value very close, 5.5 K was 5.7 K. Okay, and we do semi-correlation. This is what I showed you before. Now we have very fair comparison. Model only the quadrupling CO2, only thing changes is CO2. assume after 20 years, everything known internal dynamics. So our correlation is very, very good, 0.98 level. So our prediction correlated with model actual projection at the 0.9 level. So compared to this, I would not say better, but equally good. Also, after removed global mean, spiral pattern, remember we don't have ocean response, still very good. Okay, and so here, of course, this is last diagram here I want to show here. And in terms of course, our model doesn't have projection. We don't have ACC cooling in South Ocean, cooling or South Ocean. We also don't have ANSO. So we just use this error in this here and here. We correlate our global mean error, 0.93. Basically, you say, of course, I don't think that's really true, but statistically that's true. If our prediction could capture the cooling here and the ANSO here, we would almost perfect recapture CESM2 forecast, warming projection. Okay, so here is our summary, and the first one, our prediction capture observed warming, and so our prediction has higher map correlation with observed warming. That's comparable to historical simulation. And because we don't have ocean response, as well, we don't have other internal variability and other anthropogenic signal, the map correlation after removing global mean is noticeably smaller. But the most important I want to see here, the 1, 2, 3 strongly suggests the presence of anthropogenic CO2 increase is the primary cause of observed warming. So this is the first independent assessment from the climate model assessment, from trend analysis. When you trend analysis, you all need to separate the natural variability, signal versus noise, this kind of thing. Here, we bypass that one, independent one, also principle-based one. So conclusion reach the same conclusion. So that's what I'm happy to report that. And so next one, so we can capture the six model warming projection. Okay, the intermodal spread is smaller. Our map correlation scale is really comparable, okay, to the same six model map correlation scale with historic with observed warming, okay, and I just want 2 more slides show the limitation. I don't want to say this method work everything, but that does have a limitation because of the approximation we learn from the history, from the past. So here, the only further linearization is one approximation. And also, in this method, we cannot include ocean response. Besides this, we use history, okay, past, okay? So we need to use estimate from this here, okay? So this estimation would work, would invalid if your special pattern of the forcing has nothing to do or has a little resemblance with this mean state forcing history. Okay, here I give example. So this case work because similar here, even though not identical here, at least capture a few features similar. I want to point out large value here and small value here, relatively small value in highlighted, particularly in not here. So we try the same idea. Can we predict global warming, glacier age? This is back to a paleoclimate thing here, okay? And so we decrease CO2. So when you decrease, of course, forcing is negative. In principle, this method can equally apply for negative forcing, ambient forcing. But the thing here, if you look at the detail, negative forcing is stronger in subtropical, okay? Just a mirror image of this, okay? Less here, and polar also stronger than here, okay? Nevertheless, if I apply the same prediction, you do find global cooling. So this is almost, you removed half of CO2 from our observed state in 1980 to 2000. So you get a cooling 2.7. Then you remove 2/3 of the CO2, 4.2. I think they are underestimate. Cooling should be much stronger. The reason you can see next diagram we show here, here I plus ice line move, okay? This ice line does not move to southward very, very fast. I was told if you run your NCAR model 120 ppm, probably global would cover by ice. We cannot do that because this mean state has no ice albedo information here. You cannot make from nothing. So basically, if you give me paleoclimate warming, probably I can overestimate warming, but I can capture this melting, this kind of thing, but I cannot get freezing here. That's the end of my talk. Yeah.
You mentioned because of amplification in the atmosphere, the energy is like 200 watt.
40 watt, yeah.
Yeah.
So from the 27 to 240, yeah.
Yeah. So where does that energy go?
Okay. That's a good question, actually. The energy is used for the warming air. Okay, you don't see, after equilibrium, you don't see that part. But if you catch the warming, that's energy you need to have. So basically, if I make an analogy, I'm very exciting, so I emit more energy here, okay? So in order to get energy, I have to leave out of the room. But I have so many people here, my energy cannot leave the room. I have to warm each of you first. Then, whoever next to the window probably emit energy to the window. You follow me? So that amount of energy is here. You don't see from outside. Outside is still 27 watts. So that's how much you calculate this one. So that's something here. When we use radiation model, I also ask my question, why this has not been discovered earlier? Because our radiation model is designed, because atmosphere is continuously. We cannot calculate each layer, individual layer heating absorption. We also cannot calculate individual layer emission directly. We can calculate this table emission directly, absorption directly, but cannot calculate individual layer directly. What do? We calculate flux. We use vertical derivative to calculate so-called net cooling rate. So here we separate net by using part inverse, and we have absorption here. So that's the key. So that's depend on our method because our field is tough. It's not like physics. Physics, that's how much absorption here. You see, we do isolation, we do here, we can exactly calculate. But atmosphere, that's not how we calculate. So you have to convert net cooling rate into absorption, emission. That's key. Yeah.
Any other question? No? Okay, let's thanks Professor Cai one more time. And feel free if you have any question you want to ask him, you can ask. Yeah. And he will stay in 1 month.
Thank you.